Hi everyone. In this video we are going to derive an expression for hydrostatic force and the center of pressure for a submerged surface. So let's get started. So what you see here is an object that is submerged inside a fluid, and let's look at some of the variables that you see here. So the first thing that you see is HC, this height. So HC is the vertical height or distance from free surface to the centroid of the object or plane, whatever you can call. And YC is the inclined distance from free surface to the centroid of the plane. Okay, and then there is Y, which is again the inclined distance from the free surface to this small area df, and H is the vertical height corresponding to that. So what we are interested in is finding the magnitude of Fr. So Fr is the resultant force acting on the plane. Okay, and then we are interested in finding the point at which it acts. So that point is called Cp. Cp is the center of pressure, and we are interested in finding the coordinates yr, xr for that center of pressure. Now we are working here with respect to inclined axis. So this is our x-axis, and then this is our y-axis. Okay, so with that, let's see how we can get an expression for Fr, and we will also see how to get the coordinates where that force is acting. So we know that force is pressure times area, and we also know that the pressure, and in this case the hydrostatic pressure, is given by an expression called gamma times H. So gamma is the specific weight of fluid, and H is just the height from the free surface to the point where you want to calculate the pressure. So in this case, what we are going to do is, in order to calculate the force acting on this entire plane, we are just going to look at a very small area, and this is the frontal view of that area, and we are interested in finding out how much pressure is acting at this small area, and then we will just integrate that area to get the force acting on the total area. Okay, so to do that, what I'm going to do is I'm just going to say Fr will be the force acting on that small area, and then I integrate that over the entire plane. Okay, and then we know that force is pressure times area. So pressure will be gamma times H. Okay, so in this case we have this H acting at that. So this is the H corresponding to this point. For now, I'll just write H for now. So gamma H times the area. So force is pressure, so this is the pressure, and the area will be dA. Now we can write H in terms of Y. So this is again integral gamma times y sine theta. So theta is this angle that the plane is making with the free surface times dA. Now sine theta is constant, gamma is constant. I can take that out. So we have gamma sine theta, and then we have y times dA, and this expression integral of y times dA is the first moment of area, moment of area with respect to x-axis, okay? And that can be written as gamma sine theta times y c a, and yc is this inclined distance from the free surface to the centroid of the area, okay? So if we have that, then we can again replace yc times sine theta as gamma hc times a. So this is the inclined height yc, and yc times sine theta gives us this hc, which is the vertical height from the free surface to the centroid. And that's the expression we get for the resultant force. So we can write the expression for resultant force is gamma times hc times a. So gamma again is the specific weight of the fluid. Hc is the vertical height. So I want you to remember this. Hc is the vertical height that you see here, this height. And A is the total area of this object that is submerged inside the fluid, okay? So this is the expression that we have for the resultant force acting on this plane. The next thing we are going to do is we are going to find out the coordinates of the center of pressure, okay? So let's continue. So now we have the same figure. Now we have the expression for Fr, which is gamma times Hc times A. And now we are interested in finding expression for Yr and Xr. So Yr is this distance, inclined distance, and Xr is again the distance from the origin along the x-axis, which is this, okay? So what we are going to do now is we are going to take a moment around this point O. So this is our origin, and there are two ways we can do that. One way is to just get the resultant force Fr times Yr. So remember, moment is force times distance. So what I have done here is I have used this Fr and I have used this Yr to write this expression Fr times Yr. The other way to do that is calculate the moment for this very small area, then integrate it over the entire area, and that's what we are going to do. So either way, the total force or the total moment is going to be the same. So I write this on one side, and on the other side I take the moment. So that moment is going to be again over the entire area. So df times y. Okay, so y is again the inclined distance from the free surface to this small area that we are looking at. So for Fr we have gamma times hc. So hc can again be written as yc sine theta times a times yr. So that's our left hand side. And for right hand side we have this integral, so I will leave y as it is. And for df again we can use this expression to write df. So df will be gamma, and instead of hc now, which is the vertical height to the centroid of the total area, we can just use y in this case. So that is y, and then area will be dA. Okay. Oh, so hc instead of h, we are going to write y sine theta. So that should be y sine theta, not just y. So y sine theta times dA. So again, gamma and sine theta are constants. So I'm going to get gamma and sine theta outside the integral. And then we have y squared times dA. Now this expression y squared times dA is the second moment of area, which is basically the moment of inertia with respect to axis formed by the intersection of the plane and the x-axis. So this expression here is the second moment of area, or it's the moment of inertia forming through this axis, so Ix. So this is the expression for Ix. So what we have here is gamma times yc times sine theta times area times yr is equal to gamma times sine theta times Ix. Okay, so gamma sine theta gets cancelled. So we have a times yc times yr is equal to Ix. Okay, or yr is equal to Ix divided by ayc. Now Ix is the moment of inertia passing through this axis, and if you remember the parallel axis theorem when you studied moment of inertia, so the parallel axis theorem says that the moment of inertia passing through any axis that is parallel to the centroid, then we can write Ix as Ixc. So that's the moment of inertia passing through this centroid plus ayc square. Okay, and ayc. So instead of Ix now, which was the moment of inertia passing through the axis that was going through dA, I wrote that in terms of the moment of inertia passing through the centroidal axis, and then we get an expression Ixc over ayc plus yc. Okay, and that's the expression we have for yr. So we can write yr is equal to Ixc divided by area times yc plus yc. Okay, so what this says is that the force Fr is acting just below yc, and that distance from yc to the center of pressure is given by Ixc, which is the moment of inertia passing through the centroidal axis, divided by area times the inclined distance to the centroid. So we have Fr is equal to gamma times hc times a. So in the hc in this is this vertical height. So that's something we always want to remember whenever we are calculating the magnitude of the force. So that's the magnitude of the force, but when we are finding the y coordinate of that magnitude of force, or the y coordinate of the center of pressure, the expression that we have is Ixc divided by y c times a plus yc. So in this case we are using yc which is this inclined distance. Okay, so when we are calculating the magnitude of force, we are using the vertical distance to the centroid. When we are calculating the y magnitude of that resultant force, we are using the inclined distance to the centroid of the plane. Okay, and then Ixc is the moment of inertia passing through the centroidal x-axis, and depending on the shape, we have equations to find Ixc. So once you know the moment of inertia and yc and the area of the object, you can find out the y coordinate. We can use the same procedure to find the x coordinate, but I'm not going to do that. Instead, I'm just going to write the expression for that. So xr is going to be Ixyc times yca plus xc. Okay, so xc in this case will be the distance to the centroid, and then Ixyc. So remember, this is just the moment of inertia. Ix is the moment of inertia passing through the centroidal x-axis. Now Ixyc is the product of inertia with respect to an orthogonal coordinate system passing through the centroid of the area formed by translation of xy coordinate system. So this is a little bit complicated, but if the object is symmetric, if the plane or object is symmetric with respect to either x or y axis, then Ixyc equal to 0. If the object is symmetric to either x or y, then this goes away. Then you end up with xr is equal to xc. Okay, so this becomes very easy if you are dealing with symmetric objects, and all we have to do is find yr by using this expression, and xr becomes simple. So we already discussed that. So how to get the y coordinates? So this is where yr is. Okay, and yr is yc plus Ixc divided by yca. The small distance that you see here is given by this. So what this also says that fr always acts below yc. And that is again sort of intuitive. If you think about that, the hydrostatic pressure increases as you go down, so the force is always going to be a little bit below than what you think as the midpoint of this. So you can see the pressure is higher as you go down, so that's why the point where the force is acting is lower than where the centroid is. Okay, so these are our final expressions. So that's the magnitude of force, and the unit for this is either Newton or pound, depending on which system you are using. So that's the y coordinate of the center of pressure Cp, and this is the x coordinate of the center of pressure Cp. Okay, so that's all. So once we know the magnitude of the force, we can find out at what point it is acting by using these two expressions. So remember again here, if the object is symmetric, then xr is equal to xc. Okay, so most of the times we don't really calculate xr if you are dealing with symmetric objects. we only calculate yr. Okay, so this is all, and I hope you were able to follow these derivations. If you have any questions, feel free to email. Thank you, and I will see you next time. Bye.